Hello everyone, let's analyze. So in the last lecture we defined what compact means and then we proved that it's equivalent to the set being closed and bounded. Today however we're going to define what compact means and then prove that it's equivalent to closed and bounded. Okay, I promise this is not a rerun. Okay. In this lecture, we're actually going to give an alternative but equivalent definition of compactness, this time from a more topological perspective. So we spent a lot of time understanding limits of functions and sequences and classifying sets and whether they contain subsequence limits or accumulation points, which of course we know that those ideas are closely related by Theorem 1.17 of the textbook. But now we have a new tool for describing sets of real numbers, open and closed sets, right? In the last lecture, we learned the precise definition of what it means for a set to be open or closed. So let's consider thinking about functions in terms of this perspective, open and closed sets. Imagine, for example, that f is continuous on its domain D. Well, what does that mean? Well, let epsilon be greater than 0. Then for each y in the domain, there is a delta, which depends on y, remember, because it's just continuous. We don't know that f is uniformly continuous. All right, so there's a delta that depends on y. And if x is in D, and x and y are within delta y of each other, then f of x minus f of y is less than epsilon. In other words, the delta y neighborhood of y, which is an open set, intersecting with D, is mapped by f to a subset of the open interval f of y minus epsilon to f of y plus epsilon. In other words, the f of y neighborhood of epsilon. Or I'm sorry, the epsilon neighborhood of f of y, rather. Now imagine that I took the union of all of these delta of y neighborhoods of y for every y in D. Right, remember, we know f is continuous on the entire domain. So for every y in the domain, there's a delta that guarantees that if x minus y is less than delta, f of x minus f of y is less than epsilon. So let's let g delta of y be just a name for the delta y neighborhood of y. So, okay, it's just a name because delta y neighborhood of y is a bit of a mouthful, so we're going to call it g delta of y. And let's consider the union of all of these open neighborhoods. Now, since every neighborhood contains y, and I'm taking the union for every y in the domain, then the domain is contained inside of the union of all of g of y for all y in D. Okay, all right, so this symbol is union, but it's a union of a set of sets so that we don't confuse the ideas. Typically when we have sets of sets, we tend to call them a family of sets. And this family of sets might be indexed by many different things. Not always natural numbers the way we index a sequence. Sometimes by just real numbers. So in this case, they're indexed by members of the domain D. Now, if I could find a smallest positive value delta of y for all y in D, in other words, I took every possible delta value corresponding to every entry of D, and there was a smallest one, then we would know that in fact f is uniformly continuous. When would that happen? When would that be true? Well, that's possible if I could perhaps take a finite set of values, delta of y1, delta of y2, up to just delta of yn, a finite set of delta values. And the union of those finite number of open intervals, if the union of those finite open intervals contains D, then I could take the minimum delta value of those finite set of delta values, and that would guarantee uniform continuity. Why, do you ask? Well, I'm not going to tell you because it's on your homework. But this is kind of a new way of thinking about how the real line and subsets of the real line is warped by a function, and how we can actually describe subsets of the real line. So let's give these ideas some verbiage, some words to describe these ideas. Let's describe this idea here. This idea that the domain can be contained in the union of a family of open sets. So the family of open sets G alpha, where alpha is an A, right? So alpha is you could think of it as an indexing, except alpha may not be a natural number or an integer. It could be, well, any number of things that allows us to specify a particular open set. But imagine I have a family of open sets. I call that an open cover of a set D if D is contained in the union of all of them. So a few examples of such a thing. Let X be a real number, and let big N, indexed by little n, be the 1 over n neighborhood of X. Okay, in other words, the big N little n is the interval of X minus 1 over n to X plus 1 over n. Now, if I think about what this looks like, right, when n is 1, I get X minus 1 to X plus 1. When n is 2, X minus half to X plus half, X minus a third to X plus a third. That interval shrinks and shrinks and shrinks and shrinks and shrinks and shrinks. Well, in every single neighborhood is X, of course, because X is at the center of these open neighborhoods. So certainly X is inside of all of them, so X is, of course, inside the union. That means the family of sets of all big N little n, for all little n in the set of natural numbers, is an open cover of the set of one entry X. Now, by the way, just observe the fact that if I were to just pick big N little n for a single value of n, I would still contain the set that contains only the one element X. Okay, now let Tx be the one neighborhood of X. So for a particular X value, Tx is X minus 1 to X plus 1. So I have an open interval of length 2, right, from X minus 1 to X plus 1. Well, if I took the union of every neighborhood for every X, I would get the entire real line. In fact, the entire real line would be contained in it. Of course, it would also be equal to it because everything in every Tx is also a real number. But for the sake of giving an example of a cover, right, the family of sets Tx for all X in R is an open cover of R. Now let's consider another example. And by the way, as I go through this example, it would be a good idea to perhaps sketch out what a few of these intervals look like, maybe for n equals 1, 2, 3, 4. maybe 5 if you're feeling ambitious. Let In be the interval 1 over n plus 2 to 1 over n for every natural number n. So for example, for n equals 1, it's the open interval of a third to 1. Okay. For n equals 2, it's the open interval of a quarter to half. Notice it overlaps with the previous interval. For n equals 3, it's the open interval of a fifth to a third, which itself overlaps with the previous interval. Now I claim the union of all of these open intervals, contains, that is, covers the open intervals 0 to 1. Now could you prove it? Of course you can prove it. I believe in you. So I subscript n is an open cover of the set 0 to 1. Now, by the way, could you take a finite subset of In and still cover 0, 1? No. No, you can't. Now, while we're discussing this family of open intervals, let's note that if I were to cut off this union at some natural number capital N, in other words, take a finite number, a union of a finite number of intervals, and join to it the 1 over n neighborhood of 0 and the 1 over n neighborhood of 1, then I would have a cover for the closed interval 0 to 1. So if we go back to one of the motivating examples, we were able to give a family of open sets that covers a domain D. And then we daydreamed about the possibility of finding some finite subset of this family of open intervals that also covers D. Let's give a name to this concept. So if the family of open sets G alpha, for all alpha and A, if the family of open sets is an open cover of D, in other words, D is contained in the union of all of them, then a finite subfamily is called a finite subcover of D if D is contained in the union of this finite subset of open sets. So as an example, let's go back to our first example of an open cover, right? N little n, right? The 1 over n neighborhood of X is an open cover of the set of X. But there's a finite subcover because I could pick just one open set of this family. And because that one open set in the family is a neighborhood of X, it also contains X. So that would be an example of a finite subcover. In this example, there's no finite subset of Tx that covers the entire real line. Now, if I take the family, in the third example, if I take the family In and add to the family, right, so we're going to expand the family, the 1 over n neighborhood of 0 and the 1 over n neighborhood of 1, then I would have a cover of the closed interval 0 to 1. Okay, and we just saw here that, in fact, there's a finite subcover. So, we're now prepared to give our alternative but equivalent definition of compactness. Okay, a set E is compact if, and only if, every open cover of E has a finite subcover of E. So, upon first glance, we might say, well, this definition doesn't seem to have anything to do with the definition from the last lecture. In the last lecture, we said a set is compact if every sequence of entries has a convergent subsequence with a limit in E. So this is a very different way of viewing the real lines. But in fact, the two definitions are equivalent. Now, how are we going to prove that it's equivalent? Well, we're going to prove that this definition is also true if and only if E is closed and bounded, which is true if and only if E is compact by the previous definition. So, in order to build up some machinery, to one, just get comfortable with this idea of describing sets by ways of open covers and finite subcovers, and to give us the tools we need to prove that a set is compact if and only if it's closed and bounded, we're going to prove this lemma. Every open cover of the closed interval a to b has a finite subcover of the closed interval a to b. That is, the closed interval a to b is compact by the second definition, the one right up here. All right, let's prove it. Suppose G alpha is a family of open sets that's an open cover of the closed interval a to b. In other words, a to b is contained in the union of all of these open sets. Okay, so now we're going to define this set B, which is equal to every real number contained in the open interval a to b, and that satisfies that the closed interval a to x is contained in a finite subcover of my family of open sets. Now, by the way, if little b is contained in here, then the interval of a to little b is contained in a finite subcover, and well, we'd be done. So you might guess that that's our goal, is to show that little b is contained in the set big B. Well, before we get ahead of ourselves, is anything in big B? Well, sure, of course. At the very least, A is in B, since A is in the closed interval a to b, and because A is in the closed interval a to b, which is contained in the union of a family of open sets, then one of those open sets has to contain A. Therefore, the set from A to A is contained in a single open set. Well, so it's a finite subfamily because it's a subfamily of 1. Now, B is bounded because every entry is between or less than or equal to A and greater than or equal to A and less than or equal to B. So B is bounded, and it's also non-empty, which means it has a least upper bound by the least upper bound axiom. So let Z be the least upper bound of B, otherwise known as the supremum. Now, if we can manage to show that Z is B, and Z is contained in big B, then, well, we'd be done. So, well, let's get working towards that. Now, since A is in B, and Z is an upper bound, but B is also an upper bound of B, right? Because in order to be in big B, you got to be less than or equal to B. So B is an upper bound, Z is an upper bound. In fact, Z is the least upper bound. Okay, so A is an element in the set big B. It's less than the upper bound Z, but Z is less than or equal to B because of all the upper bounds, Z is the least one by definition. Now, by the way, notice that implies Z is in the interval A to B. Therefore, Z is in the open cover G alpha for all alpha and A. More specifically, as it's a single point, there must be at least one open set in the family. Let's call it G alpha of Z, where alpha of Z is in A, that contains Z. Therefore, Z is also in B, for one thing. Let's also analyze this open set G alpha of Z. Right? It's an open set containing Z. It also contains a neighborhood of Z, right? Because that's what it means to be an open set containing Z. It contains a neighborhood of Z, which contains an epsilon neighborhood of Z for some positive epsilon value. Of course, you know Z is in a epsilon neighborhood of Z, which is inside of the open set G alpha of Z. Now, from our alternative definition of supremum, we know, right, that there's no daylight between Z and the set big B. In other words, for this epsilon here, if I subtract epsilon from Z, then there's an element of B greater than it. Otherwise, Z minus epsilon would be a lesser upper bound. So there's some x greater than it, and that x is in B, which means it's of course less than or equal to my supremum. So Z minus epsilon is less than x, which is less than Z, and x is in B. Well, we can expand these relations. Z minus epsilon is less than x, which is less than Z. That's here. But of course, Z is less than half of epsilon, which is of course less than Z plus full epsilon. That implies the interval x to Z plus half of epsilon, that interval is contained in the epsilon neighborhood of Z, which is contained in the open interval, or the open set, G alpha of Z. And G alpha of Z is one of the open sets in my family of sets that covers the closed interval A to B. So, since X is in B, there exists a finite subcover of the interval A to X. Because, well, that's what it means to be in big B. That there's a finite subcover of this. So there are some open sets, G alpha 1, G alpha 2, through G alpha n, whose union contains the interval A to X. Now, if I take this fact and this fact together, I get A to Z. Now remember that X is less than Z, so the interval A to Z, okay, is of course contained in the interval A to Z plus half epsilon. But remember, X is, well, it's less than Z. So I can split this up as A to X, and then X to Z plus epsilon over 2. So I just split this interval in half at X. And remember that this, A to X, is contained in a finite subfamily. And this closed interval is contained in one open set, which is a member of my open cover. So the interval a to z is contained in the union of n plus 1 open sets from my open cover of the interval a to b. So because the closed interval a to z permits a finite subcover, z must be an element in big B. Okay, so we know z is in big B. We know z is either less than b or equal to b. Our goal is to show that it's equal to b. Well, suppose that's not true. Suppose z is less than b. If z is less than b, then there's a number between z and b. Not only that, there's a number that's both between z and b and between z and epsilon over 2. Let's name that number y. Okay. So y is both between z and z plus half epsilon, and y is also between z and b. Therefore, the closed interval a to y is contained in the closed interval a to z plus epsilon over 2, but we know that this is contained in a finite subcover. If the closed interval is contained in a finite subcover and y is between a and b, then y is in b, which means we have a contradiction, because if y is in b, y has to be bounded above by z, because z is an upper bound. But we assume that y is greater than z. Well, that's just absurd. That can't happen. Z can't be an upper bound of b and have an element of b greater than it. So it can't be true that z is less than b. It must be true, therefore, that z equals b. Therefore, the interval a to b equals the interval a to z, which is covered by a finite subcover. Which one? This one. This one here. And we've proven our result. And now to the main event, where we prove that this definition of compactness is equivalent to a set being closed and bounded. That's a typo. That should say bounded, which is equivalent to a set containing the limits of a subsequence of every sequence of values taken from it. Oh, by the way, this theorem, it's kind of a big deal. It's even got a name. The Heine-Borel Theorem. A set is compact using the every open cover permits a finite subcover definition if and only if it is closed and bounded. Okay, let's set about proving it. Suppose that E is closed and bounded. We're going to prove the reverse direction first. Let's show E is compact. All right, so what do we know? We know E is bounded. In other words, there's a value alpha and a value beta that is less than or equal to and greater than or equal to, respectively, every entry of E. Meaning, E is contained in the closed interval alpha to beta. We also know E is closed, which is equivalent to the complement being open. We proved that last lecture. All right, what's our goal? Our goal is to show that if the family of open sets G alpha is a cover of E, then there is, in fact, there must be a finite subfamily that also covers E. Okay, well, let's get right toward our goal. let G alpha be an open cover of E. In other words, a family of open sets whose union contains E. Now, E is contained in the closed interval alpha to beta because alpha and beta are the bounds of E. And the closed interval alpha to beta is, of course, a subset of the real line. And the real line is equal to every number in E and not in E because, well, every real number is either in E or not. Now, I know that E, right, is contained in its open cover, right? So if I take the open cover of E joined by way of a union with the complement of E, I get equality, every real number. So we have built another open cover of the closed interval alpha to beta, right? Remember, G alpha is an open cover of E. What we have here is an open cover of the closed interval alpha to beta. But we know from our lemma just a bit above that a closed interval alpha to beta, that is every open cover of a closed interval, permits a finite subcover. Therefore, I could take a finite subset of the open intervals, right? Here's one open interval, or open set, I'm sorry. Here's one open set, and then here's a family of open sets. Okay? So I can take a finite subset of these and this and get myself a finite subcover of the open interval alpha to beta, which of course contains E. Now, we're not done because I need to show E is contained in a finite subcover of G alpha. This open set, the complement of E, that's not necessarily contained in my family of open sets. I need to show that I can get rid of this. So, I can get rid of it. Why? Well, E is contained in this joined to the complement of E. By the way, the complement of E means every number not in E. So there's no element of E that's in the complement. Meaning if E is in the union of this and this, it must be contained in just this, because it's got nothing here. Therefore, E is contained in this union of a finite set of open sets. And that is the finite subcover we are looking for. Therefore, if E is closed and bounded, it's compact, using the open cover definition. All right, now suppose that E is compact. Let's show that it's closed and bounded. Okay, so what do we know? We know E is compact. Every open cover of E permits a finite subcover. What is our goal? E is bounded. It has a lower bound, it has an upper bound. Also, we know E is closed. That is, E contains all of its accumulation points. Okay, first let's show that compactness implies boundedness. Let Gn be the open interval n-1 to n+1. In other words, a one neighborhood of n. Then if I took the union of such neighborhoods for every integer n, from negative infinity to positive infinity, I would have a cover of the real line. In fact, I would have exactly the real line, which of course contains E. And since E is compact, there must be a finite subcover of this that contains E. But since each of these intervals is bounded, right, it's at most a distance of 1 from n, and I have a finite union of bounded sets, then E is bounded because it's bounded below by, well, the smallest n of k minus 1, and it's bounded above by the largest n of k plus 1. So we've shown that compactness necessarily implies boundedness. Now suppose that X is an accumulation point of V. Okay. Let's consider the closed interval of X minus 1 over n to X plus 1 over n. That's a closed interval that shrinks down to X as n goes to infinity. Right? It's the closed interval x minus 1 to x plus 1, x minus half to x plus half, x minus a third to x plus a third, x minus a quarter to x plus a quarter. It shrinks down to x. So if I take the complement of that closed interval, then I get an open set. And since the closed interval shrinks down to just x, the open complement encompasses all of the real line except for x if I take the union of every single one. Now, suppose for the sake of contradiction that x, which remember is an accumulation point of E, is not contained in E. If that were true, then E would not be closed. We're trying to prove that it is closed, so let's suppose that it's not closed and see if we can prove a contradiction. So if x is not an E, then every entry of E is a real number, not x, which means E is contained in the complement of x. In other words, the set of all reals but x. And the set of all reals but x is equal to the union for n equals 1 through infinity of Gn. Thus, the open cover, Gn, of E permits a finite subcover. How do we know that that's true? Well, because E is compact. Every open cover permits a finite subcover. So there's some finite subcover, right, whose union contains E. But notice that Gn of k is nested. In other words, there's a max value of, right, the subsets n that I take, right? I take, right, n values of n, and those n values of n, well, there's a max value. And if I take the largest one, I get the smallest interval, x minus 1 over n max, x plus 1 over n max, right? The smallest interval, but remember, I'm looking at the complement of it, so it's the biggest open set. And E is completely contained in this open set, right, which is everything except a 1 over n max neighborhood of x. Now that means there's no entries of E in the interval x minus 1 over n max to x plus 1 over n max. But this contradicts the supposition that x is an accumulation point of E. Because if x were an accumulation point of E, this interval would not only contain entries of E, it would contain an infinite number of entries of E. So we've proven a contradiction. It can't be true that x is an accumulation point of E and not contained in E. Therefore, x is an accumulation point of E and is contained in E, meaning E is closed. And we've proven our assertion. This now gives us three equivalent ways to think about and define compact sets. A set E is compact if and only if every open cover of E permits a finite subcover, every sequence of values in E contains a convergent subsequence whose limit is in E is closed and bounded. So if we have to prove a set is compact, or if we have to prove that compactness implies some other property, we're free to choose any of those three bullet points as we need. That's all for today.